Hey guys, today we're doing Chapter 10, Section 4, which hopefully is a lot easier than Section 3, so it'll be a nice little relief. Section 4 is all about normal curves. So far in Chapter 10 we've just been talking about binomial experiments. Now we're going to talk about how we can relate normal curves to binomial experiments. And in this section we're just doing an introduction, a really basic introduction to normal curves, what they look like, what the equations are. And then in the next section, we'll actually relate those back to probabilities and distribution functions. So what I want you to do is start by graphing f of x equals e to the negative x squared on the window from negative 2.5 to 2.5 and negative 0.5 to 1.5. So on my graphing calculator, I'm just going to go through, I'm going to type in that equation. So I've got e to the negative x squared. Okay, it looks like this. Alright, and then I'm going to change my window. So my window is going from negative 2.5 to 2.5 and negative 0.5 to 1.5. And this is the graph that I get. Okay, so it wants me to sketch this graph on the axis at the right. So my paper doesn't have an axis, but yours does. Okay, so this is about negative 2. This is about 2. Okay, it looks like it goes up to 1. It looks something like this. Okay, what kind of symmetry does f have? So is this function symmetric? You should notice that this has a symmetry over the y-axis. So this is reflection symmetric. Over the y-axis, which is the equation x equals 0. Okay, if I want to find the limit as x approaches infinity, well, let's think about this. As my x values are getting larger, what value am I approaching? The answer is 0. And what about the limit as x equals negative infinity? Well, as my x values are getting smaller, again, this is still approaching 0. Does this have any asymptotes? And if so, name them. Yes, it has an asymptote at the x-axis. It's never going to reach the x-axis, but it's getting closer and closer to the x-axis. So the equation of the x-axis is y equals 0. The graph also has two inflection points where the graph changes concavity at x equals plus or minus square root 2 over 2. Concave up is when the graph is curved upward. Concave down is when the graph is curved down. So these points of inflection are basically where I'm changing from going down to this scoopy going kind of up. So maybe right here and right here, those would be kind of your inflection points where your graph is changing concavity. The graph above is called the parent normal curve. So this is kind of the parent function for any normal curve. Consider the following binomial probability distributions for p equals 0.8, showing the change of the distribution as n increments from 5 to 20 to 50 to 100. So I don't have it up here, but I do have it on your paper here. And looking at the first graph, it's kind of hard to tell what's going on in that graph. But as we continue moving up and up and up, you should notice that we're turning into more of this bell curve here. And you should also notice that this has a probability of 0.8. Okay, that's like 80%. And each of the highest points of this graph are around 80% of the number of trials that I have. So that would be your mean. Remember that the mean of a binomial probability distribution is n times p, so the number of trials times the probability. So if I had 20 trials, it would be 20 times 0.8, which would be 16. If I have 50 trials, it would be 50 times 0.8, which is 40. And if I have 100 trials, it would be 100 times 0.8, which is 80. So you'll notice that the tops of each of those graphs fall at the mean. As you can see, as n increases, the value of a binomial distribution approaches those of a normal distribution, taking the shape of the parent normal curve we looked at above. So all of these are getting closer and closer to this parent normal curve. Many natural phenomena have approximately normal distributions. Some examples from the book are heights of people from the same population, amounts of rainfall for a certain city over long periods of time, and weights of individual fruits from a particular orchard in a year. So normal curves are actually really nice because we can generalize certain situations using normal curves. The parent normal curve gives rise to the standard normal curve or standard normal distribution, which, because of its properties we'll discuss below, will allow us to determine probabilities. Okay, so this parent normal curve that we just talked about, we don't really care about it. Okay, it's just kind of the parent function for this standard normal curve. This one is the important one because we can use it for probabilities, and we'll talk about that in the next section. So for now, we just want to look at the equation of this and look at some of the properties, and then we'll actually use those properties later on. So the equation for the standard normal curve is f of x equals 1 over the square root of 2 pi times e to the negative x squared over 2. Looks nasty, you don't have to memorize it, don't worry about it. Okay, it's the image of the normal curve under a scale change of square root of 2 times x and y divided by the square root of 2 pi. So if we want to sketch that on the axis to the right, you can go ahead and graph that on your graphing calculator, and what you should get is something like this. Okay, so notice that it doesn't even go all the way up to 0.5 for this middle probability here, and it's still extending past -2 and 2. So let's look at some properties of this. What kind of symmetry does F have? It has the same symmetry as before, so it's reflection symmetric over the y-axis. Okay, the limit as it approaches infinity, while as my z values are getting bigger, I'm going towards 0 still. As my z values are getting smaller, I'm going towards 0 still. So it's the same thing as the parent function. Does it have any asymptotes? Yes, it still has an asymptote at y equals 0, just like the parent function did. And this one, they tell us the inflection points occur at plus or minus 1. So you'll notice that at 1 here, that's where it's changing concavity for both of those sides. So that those concavity points are much better. Finally, the most important of all is that the area under the standard normal curve is 1. So under that entire curve, that area is 1, and that's why we're going to be able to use it for probabilities. And that's everything for section 4.